right, let's talk about rational functions. Now, in previous videos, we've talked already about the domain, x-intercepts, y-intercepts, the holes and vertical asymptotes. This third video in a series here is going to talk about horizontal and slant asymptotes, graphing, and the range of our function. So let's get right to it. Let's talk about what a horizontal asymptote or why they're going to occur. First of all, we've talked about end behavior of our graphs before. Remember, the end behavior is where we're traveling left and right on our graph for very, very, very large, right? What kind of x values are we looking at? Large positive and negative x values out to the right and out to the left. So end behavior of our graph is saying, are we going to travel to infinity, right? Up or down, negative infinity, or are we going to flatten out? And that's really where horizontal asymptotes come from. Now, what's most important in our function? Well, when we're looking at a polynomial, the thing we always try to identify is that term of highest degree. And you'll notice by plugging in really large values here, that the term of highest degree, that x to the fourth, is really ruling the roost. When we plug in things like 500 or 1,000 or even a million, we get much larger values for those values than we do for any other term of our function. So the term of highest degree rules the roost. Well, in that case, when we compare terms of highest degree, when we're comparing polynomials, right, ratios of polynomials, what's going to matter is where is that term of highest degree? Is it in the denominator to where the bottom of a fraction might be getting very, very large? And again, feel free to pause the video and read through the questions here. I'm going to move fairly quickly because I want to make sure we get through lots of information here. But again, when the term of highest degree is on the bottom, x plus 1 versus x squared plus 1, or such as d of x here, right, x over x squared, only those terms of highest degree, right, are going to matter. And if it's on the bottom, then basically we're always going to be traveling towards 0. If they're equivalent, right, 2x plus 1 over x plus 5, well, again, those plus 5s and plus 1s aren't going to matter so much, right, those constants. But again, x compared to x, well, they're going to kind of run the race side by side. Only the top will always be about twice the size of the bottom. So that's why we would have a horizontal asymptote at y equals 2. Or basically compare, right, when they're even degrees, equal degrees, probably be a better way to word that, equal degree, then we'll compare the leading coefficients. 2 over 1, right, would make y equals 2. And then finally, if the top degree is larger, then the fraction is just going to flat out get large. It's going to go toward infinity, and we're going to have a no horizontal asymptote. Note that if our top degree is exactly 1 greater than the bottom, we'll talk a little bit about there is such a thing as a slant asymptote. So rather than going toward a horizontal line, it'll actually follow a different line, right, as we follow ourselves way out to the right and way out to the left. Let's talk about the 3 different examples that we've talked about previously. And again, I'm going to move fairly quickly using those rules we just came up with. If we have x squared compared to 2x squared here, then I can immediately add to our list of information that we're going to have a horizontal asymptote at y equals 1/2. So I'm going to draw that line into my graph because we also want to add our function today. We're going to talk about how to actually graph this. I'm going to take all the rest of my information as well. I'm going to put that on my graph. So we've got our vertical asymptote. Note again, our asymptotes are drawn with dashed lines. Never a bad idea to label them as well. So again, y equals 1/2 here. We have a hole at 2, -5, right? And then we have x-intercepts at -3 and y-intercept at -0.6. And that's really enough information for me to follow my line through my points toward the hole, skipping over the hole though, and getting that left branch of my hyperbola. Now you can plug random numbers in to the right side. I'm going to go ahead and use some symmetry here. From where my 2 asymptotes cross, I notice that my hole is exactly 5.5 points down from my vertical asymptote. So I'm going to move another 0.5 point to the right. I'm going to go up 5.5, up to 6 here. And I'm guessing if you check, when you plug in 3 into our function, right, and feel free to pause the video and do so, you'll get the 0.36 on our graph. Same thing goes here. If I go 2.5 to the left of there, I'm going to be down about 1.1, right? I'm up at 0.5, but I'm down at -0.6 for the y-intercept. So if I go about 1.1, I'm in good shape there. Well, let's go right. 1/2 makes 1.5 makes 2.5. Then I'm going to go up 1.1 and I'm going to plot a point there. If you double check, I'd be willing to bet, again, when x is 5, that we're going to be up at 1.6. So feel free to check that on your calculator. Again, following those points, we've got our branch of our hyperbola. And again, you could always use the table on your graph, or on your calculator, I should say, the table on your calculator to plot a lot of extra points as well. But again, we just need enough points to get a good idea of where our graph is. Again, I'm also going to note what I'm counting by. I counted by ones on my graph, so I'm going to put some labels on there, and that's a pretty good looking graph. Let's move to our next example very quickly here. We've got our horizontal asymptote. Again, I'm going to compare the leading coefficients. Notice that the degree of the bottom is larger. That means we're always going to go towards 0, right? That the numbers as x gets really, really big, right, way to the right and way to the left, are always going to make really, really tiny fractions. So y equals 0 will be my horizontal asymptote. Now I'm going to get the vertical asymptotes, right, plotted. So at 2 and -1. We're going to want some extra points. So I'm going to go ahead and start a table very quickly here. When x is 3, right, and I'm going to save myself some time. I'm going to get rid of that common factor where the hole occurred, right, at 1, -1.5. May as well plot that hole on our graph. You can plot it a little more accurately than I did. That's kind of large for that point there. But again, we've got a few points that we can plot. But at 3, again, just past that vertical asymptote, it looks like I'm going to be at 7, right? 2 times 3 plus 1 over 3 minus 2 would be 1, plus 1 would have been 4, so about 7/4. So I'm going to be up at about 1.75. And I believe, other than plotting maybe a point when y equals 1, trying to be a little more accurate there, that should be a fairly accurate line. Right? More points, again, would always be helpful. You could also plot off to the left of -1. So maybe I'll plot -2 over here. -2 would make for -3 over. Again, we're down here on the bottom is going to be a -4 and a -1, makes for +4. So at -2, I'm going to be at -0.75. Follow the horizontal asymptote. Curve to follow the vertical asymptote. We want to get just a little closer to those two lines as we're going. And that gives us a good graph there. Now this does add a slight trickiness to it. If you take a good look at your x-intercept, it's actually at -0.5, which means we do have a point on the horizontal asymptote. That's okay. If we plot our y-intercept as well, right, down at -0.5 here, right, you can cross the horizontal asymptote in the middle of your graph. Remember that the horizontal asymptote is more of a limit out to the right and out to the left on our graph. We can cross it in the middle, we just can't cross it way out to infinity and -infinity, left and right. So realize that is a little bit tricky, but it does work. Okay. Again, I'm going to move fairly quickly into that next graph. This time, taking a look at the top and bottom, we've got x squared over x. So remember, if the top degree is larger, we say there is no or horizontal asymptote, right? None. But because it's exactly 1 greater, this is where we're going to have that slant asymptote. Okay? And to find the slant asymptote, all you have to do is a little bit of synthetic division. If we actually divide x squared minus 1x minus 2 by x minus 1, right? +1 being what we're going to divide by then. We do the synthetic division. You'll notice what we get down here, right? Y equals x, technically plus 0, and then minus our remainder. Well, remember, when x is really, really, really big, this fraction is going to get really, really, really small. Or basically, that goes to 0 as x goes to infinity, right? Or -infinity for that matter. So that's going to disappear. I'm going to ignore that remainder, and my slant asymptote comes from the rest of my equation. So very simply, I'm going to have a slant asymptote right here. I'm going to have a vertical asymptote, again at 1. And if we follow our points here, x-intercept at 2, 0, y-intercept 0, 2, and another x-intercept at -1, we can follow the slant asymptote upwards, and we can follow the slant asymptote and the vertical asymptote, And you'll notice that this time our range then from top to bottom would be all real numbers, or in interval notation, negative infinity to infinity, right? Because we're infinitely going up and down. There's not a y value that's not represented. If we backtrack a little bit here, the range of our other functions, we'll notice we'll never hit y equals 0. So our range would have been from negative infinity up to 0 on this graph, skipping 0 and going toward infinity, right? Or all real numbers except 0. And then finally, to backtrack onto this graph, oops, and actually we're fine there. The range on our first function, right? Again, we have to avoid that horizontal asymptote. So looking back to where that was, again, we're going to be all real numbers such that y can't be, right? It's never going to touch, right? 1/2. Now that brings me back to the fact that, well, wait a minute, if I just can't touch that horizontal asymptote for that middle graph, wait a minute, didn't we cross that right in the middle of our graph here? Which means technically we did hit 0. I'm going to go back, I'm going to backtrack a little bit here. You have to be a little bit careful. It's always easiest to look at your actual graph. Notice that y doesn't hit 0 to the right and left, but it does in the middle. And then where the hole was, we also have a point on the left branch with the same y value. All y values, I'm going to say, all real numbers, all the y values are represented on this graph. So again, your range can be a little bit tricky. Make sure you look at the graph to help you out. If you have any questions, make sure you talk to your teacher. Otherwise, have a great day.